Most of the mass in the universe is something completely invisible, and while the mainstream idea is that dark matter is some kind of undiscovered particle, it's also possible that it's lots and lots of primordial black holes. This isn't a new idea, and in fact, we've managed to rule out most of the mass ranges at which these PBHs could account for dark matter. But there is a mass window remaining. PHBs with masses of 10 to the power of 14, 10 to the power of 20 kilograms, or a medium to largish asteroid, aren't ruled out by observations, and so might account for dark matter. And if dark matter is made of PBHs, then the black holes would need to exist in such enormous numbers that it's not crazy that some would end up inside stars. The other motivating factor is gravitational waves. We've now observed 100 S-mergers of black holes by the tiny ripples in the fabric of space-time generated in the last second of their inspiral. These mergers were probably of black holes created in the deaths of massive stars, but there are some niggling inconsistencies with the sort of black holes we expect from stellar deaths that might be explained if some of these mergers are instead primordial black holes. So there's some frankly pretty tenuous reasons to think there might be lots of primordial black holes out there. But the implications of one of them getting into the sun are pretty fun, so let's dig into it. One of my favorite fictional astrophysics catastrophe scenarios is the sun being consumed by a black hole. Fortunately, the chance of a black hole randomly wandering into our solar system is pretty tiny. That's good news. But what if it's already here, hiding in the core of the sun and slowly eating it from the inside out? Once upon a time, we really did think there just might be a black hole in the heart of the sun. And by we, I mean a small handful of scientists that, at least for a minute, included Stephen Hawking. In a 1971 paper, Hawking pointed out that we wouldn't even know if the sun was hiding a black hole with a mass of up to 10 to the power of 14 kilograms. Sounds unlikely given that black holes are supposed to have masses at least 20 trillion times larger or a few times larger than our sun. But in that same 1971 paper, Hawking also alerted us to the possibility that countless much smaller black holes might have been created in the very early universe, what we now call primordial black holes, which we've discussed on multiple occasions. So what if one of those somehow ended up inside the sun? Today we're going to talk about whether or not our sun, or indeed any star, might harbor a captured primordial black hole, what this would do to the star, how we might figure out its presence, and why this could tell us the nature of dark matter, of all things. First up, let's talk about why Hawking's idle speculation captured the imagination of a number of astrophysicists. It's because a black hole in the sun's core offered a solution to a major conundrum about our star's behavior. By the middle of the last century, we thought we understood the fusion reactions that power the sun very well. Under the temperatures and pressures that we knew must exist in the sun's core, hydrogen should fuse into helium at just the right rate to produce the amount of energy needed to power the sun. Those reactions must also spray a ludicrous number of neutrinos out into space, and checking that the sun was blasting out the right number of neutrinos was to be our nail in the coffin confirmation of our model of the sun's interior. The first neutrino detectors came online in the mid-60s, but the number of neutrinos came up short by a lot. Only about a third of the expected number of neutrinos were observed. This was the solar neutrino problem. One proposed solution was that the sun does not generate all its energy through fusion. Perhaps some of its radiation came from a non-neutrino producing source. Then a few years later came Hawking's idea of black holes inside stars, and with it, a potential new power source for the sun. Now you might think that a black hole would suck energy out of a star rather than provide energy, but that's not the case. Black holes are actually at the hearts of the most efficient engines in the entire universe. While matter and energy that crosses a black hole event horizon is lost forever, matter approaching the black hole can reach speeds close to the speed of light. This results in crazy friction between infalling streams and correspondingly crazy temperatures. So a feeding black hole glows bright. For example, quasars, powered by truly vast black holes in a feeding frenzy, are among the brightest objects in the universe. A black hole in the heart of the Sun would gobble up some of the matter, but plenty more would be blasted outwards as radiation. That way, the Sun wouldn't need to be fusing nearly as much hydrogen to reach its energy output, and so also wouldn't produce as many neutrinos. Cool idea. Except then, we figured out the real reason for the solar neutrino problem. It turns out the Sun is producing exactly as many neutrinos as we predicted, we just weren't detecting all of them. Neutrinos oscillate between their 3 different types, and our detectors were only sensitive to one of those types. With neutrinos accounted for, the black hole engine was no longer needed. There's still the nagging issue that if primordial black holes exist, they could still end up inside stars, and we would never know it. And in the decades following Hawking's paper, we only found more and more motivations for primordial black holes really existing. The first is another big conundrum like the solar neutrino problem, except this one hasn't been solved yet. It's dark matter. In fact, 2 papers appeared this week. Both papers contain new state-of-the-art simulations of sun-like stars that capture primordial black holes during formation and follow their evolution all the way through some pretty unique life phases until they're ultimately swallowed by their black holes. They refer to these black hole-harboring stars as Hawking stars after the guy who first set us down this crazy line of reasoning. The evolution of stars without black holes has been well understood for many decades. A giant cloud of gas collapses under its own gravity until the core reaches a high enough pressure and temperature to fuse hydrogen into helium. The star is born, and that core self-regulates to fuse somewhat consistently for billions of years. Once the fuel for that fusion is used up, the star goes through a series of death throes. For a sun-like star, that means puffing up to red giant, then entering a helium-fusing stage, then ripping itself to pieces by overdoing the fusion energy production to leave behind its exposed core as a white dwarf. Let's now add a black hole into the mix. The papers in question simulate what happens if a primordial black hole with the mass of a medium-sized asteroid happens to be in the cloud of gas, so the star forms around it. This stuff also works for a star that captures a black hole after its formation. A black hole with the mass in question is minuscule, the size of an atom, and its gravitational reach is limited. As a result, it has no effect on the formation and early life of the star. It sinks to the center of the star and begins slowly feeding. What do you think about it? Comment down your view, like and share this video, and subscribe for more similar educational videos.